before we proceed ahead with understanding the type of interaction that electromagnetic radiation has with the material, let's quickly recognize, we had this chart or this figure that showed the whole range of electromagnetic spectrum, and some aspect of where it can be used was listed there, but it doesn't hurt us to just review one more time. In the spectrum, actually you see that we are in this specific medical imaging systems, right? In this particular course or in this area, what part of electromagnetic spectrum is used, and you will see that it is actually exploiting, from your radio frequency wave to high energy, right? You have gamma. Okay, so let us quickly look at that one more time before we start to talk about the interactions. And that is there is a reason why I wanted to do this, because first and foremost, the X-rays and gamma rays, right? If you look at the electromagnetic spectrum, right, after the visible light, as the energy increases, you see that we will exploit X-rays and gamma rays in the modalities of X-ray CT in the first part, and then later in the nuclear medicine, right. So, we will use X-rays and gamma rays. So, these are high energy in kilo electron volts to mega electron volts, and these are ionizing radiation. So, that is the reason we said we could think about the medical imaging systems as based on ionizing or non-ionizing, right. Non-ionizing, we talked about MRI and ultrasound, remember. So, now okay, so that high energy part, the ionizing part, we know where we are going to use, and then on the lower side, if you see, you have your radio waves, right. Which modality uses radio waves, right? Imaging system. Well, radio waves are used in MRI. Oh, we said that it is MRI is to do with some magnetic resonance. What does radio frequency, right, radio waves have? Why is it used? Well, it turns out to stimulate the nuclei, right, to spin one way and then to record the response. So, when you stimulate it, you again get another electromagnetic. So, you get another radio frequency. So, radio frequency is heavily used in MRI, both to stimulate and receive the response. Okay. Then of course, visible light, I mean, apart from the intuitive thing, right, in medical imaging system, you want some radiologist or a practicing doctor to look at the image. So, visible light is useful, right, it is used in medical imaging. In fact, all the modality, all the energy, all the different imaging system, in the end your output is going to be in the visible range, right. But beyond that, what do we mean? Oh, we mean that it is actually used when you have again recall what Roentgen did, right. He named it as X-rays because there was mysterious rays that were coming. He was working with Crookes tube, and so he noticed that the photographic film actually got spoilt due to some mysterious rays. So, he named it as X-rays. So, clearly X-ray can spoil a photography film, but to capture X-rays, that means to detect X-rays, by itself it is inefficient, and therefore, in order to improve the efficiency, you will exploit the visible light photons, okay, photons in the visible light region. So, we will look at. So much is clear. So, you can actually look at the different variety of electromagnetic radiation that will be involved, that will have interaction with the body. Okay. One thing to appreciate before we jump in, therefore, if you look at this from strict point of electromagnetic radiation interaction with body, right, it does not really matter whether it is whether it is X-rays or gamma rays, both are ionizing, both have higher energy here. So, from the point of view of, if you have to understand the interaction of the energies which is in this range with the tissue, probably that is fine, there is not much distinction. But where the distinction between the different modality comes into picture is the origin of this energy. So, in X-rays, where is the origin? We just saw, right, Bremsstrahlung and characteristic, whereas gamma is due to, so or in other words, it is from the electron cloud, whereas gamma rays comes from the nuclear, radioactivity from the nucleus. Remember, so the point of origin is different for both the signals, both the energies. That is the difference. Otherwise, their interaction is nothing but, oh, it's a photon, with that energy it is going to interact with the material. Okay. So, the creation is the difference. How you get this X-ray, how you generate this X-ray, how you generate gamma rays, that is different. But once it is generated, how it interacts with the body, the ionization, all that, whatever we are going to cover now for X-rays specifically, most of it can be borrowed, right. Similar interaction happens for gamma rays as well. So, we will defer gamma rays and the details of that when we get to nuclear medicine. For now, we will talk about X-ray interaction with the tissue, because that is what is important for us. Okay, so what are the, there are several levels of interactions you could talk about. Broadly, there are 3 interactions of interest. Like you see here, one is photoelectric, another is Compton scattering. All of these are, we will go into the details. And then there is pair production. So, these are some of the common 3 main types of interactions. In fact, going forward, we will rule out the last one, pair production. So, these are all interaction of electromagnetic radiation with material. So, you will have pair production, but to have pair production, it requires high energy, requires at least 1.02 megaelectric volt. So, this one, given that we are going to deal with our X-ray imaging system or even gamma rays, we are not going to really go beyond this range, like kilo electron volts, hundreds of kilo electron volts, and therefore, for our purposes, right, for practical purposes in medical imaging, we will not be bothered about pair production. Therefore, we will not cover this anymore. This is just for the completeness. There are 3 types of interactions. For biomedical application, we do not really worry about pair production. We just leave it at this stage and say that is not going to be encountered because of the high energy of the incident photon that is needed. Okay. So, now we will jump into the 2 other things. So, what is photoelectric effect, right? In some sense, before, because there are going to be several key names, unique names that come out, right. But before you get that, if you really look at it, what we have covered, right, what we covered is particulate interaction with the material. So, there we talked about roughly 2 things. One is the electron kicking out and then characteristic coming in, characteristic radiation coming out. The other is the electron with energy goes near the nucleus, right, but then it does not get annihilated and changes path, reduced energy, and that difference in energy comes out as again X-ray Bremsstrahlung radiation. So, now what is different? Oh, difference is not a particulate that is carrying energy. Now, you have a photon with that energy. So, what are the guess that we can make already? Material is material. Now, instead of a particle that is coming in, I have some energy coming in. So, what can happen? Oh, the same energy can do similar thing, right? The same energy can come in and then perhaps it can knock out the K shell electron, right? And then, oh, after it excites or ionizes, you have characteristic radiation. That is one possibility. The other possibility, the energy is coming, right? The photon energy is coming. Maybe it bumps off the outer. It does not really get into the core. It just knocks off something, right, at the outer electron shell. In which case, what will happen? Oh, it will just knock that out, reduced energy, it will just go in a new direction. Intuitively, this is very similar to what we did for charged high energy particulate, right, electron that is coming in an interaction with the matter. Similar thing happens here. So, incoming photon, in photoelectric effect, incoming photon is completely absorbed by the atom. That energy is absorbed, and then that energy, when the atom is absorbed that energy, if it has greater than the binding energy, it will kick the k electron out. When it kicks that, or even L, and then there is going to be characteristic X-ray produced. Again, that characteristic X-ray is also going to be a electromagnetic radiation. Okay, but obviously you can guess that it is going to be probably of a lower energy, right? That much is straightforward. So, if it is Compton scattering, as the name suggests, at least this name suggests, scatter means directional, something to do with bouncing off in different directions. That is why it is scatter, right. So, the incoming photon changes its direction. So, it loses energy and changes direction. So, let us go one step at a time. Let us talk little bit more on the photoelectric effect first, and then we will talk about Compton scattering, and then try to compare these two and make a final take home message of what is favorable, what is unfavorable, what is needed, what we need to maximize, what which effect we need to minimize, all that we will summarize. Okay. So, as we talked just now, an incoming photon interacts with the, so think about it this way, you have an atom, right. So, it has a core nucleus and then it has electron cloud, H mu comes in, that comes in with X-ray energy. When it comes in, it interacts with the Coulomb field, the electrical field that is there, the electron field that is there. When it interacts, what does that mean is, it is losing energy. So, in fact, the whole of H mu is absorbed by this atom in this field. Okay. Once that field gets that energy, if it has energy greater than the binding energy of K or L shell, that electron is going to go out. That electron is called as photoelectron, because you have photoelectric effect. So, this electron is coming out because of photoelectric effect. This electron is called as photoelectron. This photoelectron can do what we studied before, right. That is an electron which has energy. So, particulate, it can go subsequently do whatever interactions we already covered for particulate, right. So, that is one thing. So, the atom is completely absorbs incident photon and all energy is transferred. So, now after the photoelectron leaves, what will happen? Oh, this has to rearrange, right. All the electrons now will rearrange, because there is a hole in K shell, that electron has left. So, there is going to be realignment, exactly similar to what we covered already, right. So, the so rearrangement will take place, but the photon electron, right, the photoelectron that propagates, it went with a energy. What is that energy? H mu, it came in, this is your binding energy. So, whatever is came in minus the binding energy is the energy with which that photoelectron is going out. Clear? So, after that what happens? The affected atom comes back to its ground state. When it tries to comes to its ground state, it releases energy, and that energy, right, is in the X-ray range, and we talked about why it is characteristic X-ray, right, depending on which electron, which shell is migrating and the rearrangement pattern. Okay. So, that is your characteristic X-ray. So, now you have, of course, characteristic X-ray will also be of lower energy, right. So, now you have both the photoelectron that can go and cause subsequent interaction, and X-ray, characteristic X-ray that can also interact further. Clear? So, very similar to what we did in the particulate, right. So, here also what can happen is, this characteristic X-ray that is coming out, right, that characteristic X-ray on its way out from the atom can probably kick out the outermost atom or the electron in the outermost shell. So, you have a characteristic X-ray that is produced in the photoelectric effect. That characteristic X-ray energy, that is when the photons with that is trying to leave the atom, right, coming out from the atom, it may probably knock off the electron in the outermost shell, because outermost shell, the binding energy is going to be less, right. So, it is going to be weak. So, maybe it has sufficient energy to kick that atom. So, sometimes the characteristic X-ray transfers this energy to the outer electron. So, what happens then? Oh, then this electron gets that energy and it can move, right. So, it is an electron, charged particle, right, electron that is going to move, take some energy with it. So, this kind of electron is called Auger electron. So, the interaction is going to be same, electron with some energy, it is going to interact with the material like we discussed. So, whether it is photoelectron or Auger electron, their interaction with the material is going to be exactly same as what we already covered with particulate interaction. Only thing is, now even when we have a electromagnetic radiation carrying X-ray that is interacting with tissue, you can get these particulate radiations. So, here it is called as Auger electron. So, essentially both Auger electron and photoelectrons can interact with the matter in ways that we already covered, right. Okay. So, that is good. So, now what we need to do, okay, photoelectric effect seems to make sense. Let us just complete it with a picture. This is kind of a review, right. Text sometimes might be boring. So, just quickly to review. So, you have an incident photon h mu, some energy is coming in the X-ray range. This is your nucleus and these are your electron cloud. So, it knocks off, right, it basically the full incident photon gets absorbed completely by the atom in this field, and then it has enough energy greater than your K shell, then the K electron, the electron in the K shell will be knocked out, right, but it is given a name called photoelectron because of the process with which this electron was generated. So, once that happens, excited state, right, this is ionized. So, it will basically now try to come back to ground state by rearrangement of the electrons from outer shell to inner shell, and that gives you your characteristic radiation. Similarly, if you have the incident photon, exactly do what we did here, so much is so good, but in addition, if this characteristic radiation, right, when it is coming out, if it knocks out another electron on its way of the same atom in the outer shell, then that electron is called as your Auger electron. Clear? After that, Auger electron or photoelectron are nothing but these are electrons, charged particles, particulates with some energy. That energy, it is going to interact with subsequent atoms in the manner that we already covered. Clear? So, let us use the same sketch, right, to also talk about the other effect, which is Compton scattering. So, here what happens, incident photon comes, but notice it is not going into the Coulomb field, right, it does not go close here, but it so happens that when it comes here, it is able to hit a electron, share some energy to that electron and kick that outer electron out, release that outer electron. So, when you do that, the incident photon loses energy to the Compton electron. So, it is now reduced energy, and with reduced energy, it after the deflection here, right, after kicking that here, with the new energy, it reflects, it scatters to a different path. Here in the illustration, if this was the original path, it is deflected by angle theta, and the electron that comes out because of Compton scattering is called as Compton electron. After that, this Compton electron could do the same thing. However, notice that the energy of the Compton electron is going to be small, but from a principal standpoint, yes, this is a particulate with energy that can go do subsequent interactions. So, likewise here you have Compton photon. What is Compton photon? Oh, it is still the photon, but then it is reduced energy due to Compton scattering. So, Compton photon is the incoming energy that is reduced due to Compton scattering. So, it has lost some energy, right, in this interactions, and it is reduced, and it is at a different path, different angle now. Okay. So, Compton scattering is an incoming photon ejects a valence or the outer shell electron, yielding a new energetic electron called Compton electron, and the incident photon is not completely absorbed by the atom. The incident photon with reduced energy it changes direction. So, it does not, this is the key, it is not completely absorbed by the atom, and so this can essentially go, from here. If the Compton photon has enough energy, it can do photoelectric effect, right. It's just that after this it proceeds. Clear? So, that is for your Compton scattering. So, what we would like to do is just before we proceed ahead, let us look at this energy. So, because we said Compton scattering, it has a new angle and it is reduced energy. So, is there a relationship that we can form between the incoming energy reduced, that is your Compton photon energy, and the angle at which it is getting reflected, right. So, the energy of the scattered photon or the so called Compton photon is given by this equation. What do you see here? This is the incoming h mu, right, incoming photon, it had a energy h mu. This is your Compton photon energy. Look at how these two are related. There is this theta. Of course, m naught c square you can calculate, that is your rest mass of your electron, right. Based on that you can calculate that. So, if you really look at it, we know this energy is going to be less than this energy, but how much less depends on theta. Okay. So, intuitively speaking, if there is no change in path, right, then h mu will have, h mu dash will be same as h mu, right. It has, there is no interaction taken place, it is not lost any energy and changed the path, right. 0 means it has not changed any path, that means it probably did not interact, and therefore, there is no energy lost, and therefore, you will get the same energy. So, on a so thinking in that spirit, when will it have lost most energy? Oh, look at this, you have a 1 minus cos theta. So, it would have lost most energy when you have a back scatter, what we call as back scatter, 180 degree shift, right. So, when it comes back in the same direction, in that scenario you will have back scatter when you have maximum energy loss, right. So, maximum energy loss occurs when the photon is deflected. I mean, it is actually deflected is deflected means it is a small angle, but we for explaining this, it is like deflected, but the deflection is backwards 180 degrees. So, it is essentially a reflection, it comes back in the same direction. Okay. So, which is called as back scatter, 180 degree back scatter. Why are all these important? We need to know this because in a moment we will actually do that. We need to understand which phenomenon is favorable to our task. What is our task? Imaging, that is, we want to send the X-rays into the body, the X-rays will interact with the body, and I will receive, right, the X-rays that are coming out of the body. So, it is through transmission, and based on what I am detecting, I should comment on what is there inside the body. Clear? That is the objective. So, we need to now quickly understand what is favorable, what phenomenon is helpful for us, what is not, how to use, minimize the bad guy, maximize the good guy, right, that we need to still do. So, of course, Compton angle is one thing, and then what is the reduced energy? reduced energy is, so your Compton electrons will have an energy which is incoming minus Compton photon energy. That energy is given to the Compton electron. Okay. So, the kinetic energy of the Compton electron is the difference between these two. So, one of the ways this will be useful is, like I said, we want to send the photon through the body and collect it when it comes to the other side. If you have Compton scattering, then what is going to happen? Oh, it is going to take a different angle. So, I might sit on the detector thinking something is coming in this direction, but because of the interaction with the body, if it goes there, right, that is not going to be helpful for me, because I am not going to get it, I am not going to get the signal, right, I am not going to get the photon to make any sense of what it has interacted, right. So, Compton scattering, in that sense, it will be helpful, right, to understand even if there is a, what is the angle, right, beyond which my detector may not detect it. So, anything beyond that, it is only the body that is getting all this ionization, but your detector will not get it, because you are looking at the detector thinking it is going to come here, but because of Compton scattering it is going there, right. So, you need to know what is an angle of this Compton scattering, right, until which you probably can detect. Even if it is at some angle it can detect, but if it is greater than certain angle, maybe you are not going to detect, you are just going to dose the patient, right. He is going to have ionization, but you are not going to catch the photon to say, what about the material that came through. So, in scenarios like that, it is probably very useful to calculate this angle. So, I am not going to do that here. This is a simple substitution that you can do. So, a typical scenario is you have a incoming photon, right, with some energy of 100 kilo electron volt, and then we also say that it exits from the material with a reduced energy of h mu dash. So, now we are also saying that the detector threshold of h mu dash. So, if the detected energy of h mu dash, if it is greater than 98 kilo electron volt, so you are sending in 100, you are receiving 98 after the photon has gone through the medium. You say that if I am able to capture 98 kilo electron volt, then whatever scattering has happened, the angle of Compton scattering is acceptable. Until then you are okay, because you are capturing the signal 98 kilo electron volt. Anything beyond that, you will have to look at design aspects. So, the question is, what could be that maximum angle if this is the scenario? So, I am not going to do it now because it is straightforward. So, you will do it. What do? You are given h mu, you are given h mu dash, right. You are given h mu, you are given h mu dashed, you know m naught c square, you have to find out theta. Okay. So, if you do that, what is the maximum angle by which the photon is scattered, but still being treated as travelling in straight line path? If you calculate, it will turn out to be about 26.4 degrees. So, essentially even if it is deflected, right, straight line path is 0 degree. So, even if it is deflected by in this case about 26.4 degree, you will still be able to catch the photon in the detector when it is coming through. So, you can say that it came through the straight line. Anything greater than that probably is not going to be helpful from your signal detection point of view. Okay. So, now let us just compare the two effects, right. What do I mean by compare the two effects? See, you do not have control over any of this, it is all statistics, right, population based. So, you send some energy. Remember, when I say send some energy h mu, that h mu is not like discrete that you can. So, it is coming from an X-ray tube, and we saw in the previous lecture, basically you get Bremsstrahl lung, you get a population, right. So, you have different energies that come. In fact, sometimes you also have characteristic X-rays energy that is coming in. So, you have a host of different energies that are coming in. So, different H mu's that are coming in. So, in that sense, different H mu's are coming, different energy levels are coming. It has to interact with the body. So, there are two prominent interactions that we are worried about. One is Compton, the other is photoelectric. Which one does what? What is, which condition favors or which factors favor each of the effects, and which effect are we interested in? What is our task, right? That is what we want to do here when we compare. So, photoelectric effect helps to differentiate different human tissue organs. What does that mean? Why is that statement made? Okay, so the idea is this, right? You are sending an energy, it is going through, it is, I'm just using simple chest X-ray kind of example that you are probably familiar. Similar concept works for CT as well. So, right, so we will not complicate that. So, simple chest X-ray that you are familiar, you went and stood in front of X-ray tube, X-ray photons came in, and behind you there was a detector. So, that was detecting the X-rays that come out. So, what does photoelectric effect do? That means you have energy that is coming in, the energy is now deposited in the tissue and the remaining energy comes out. So, it is the relative distribution of which location can stop how much X-ray. That is what you see as the image in your X-ray, right. So, in that sense, photoelectric effect, what does it do? Oh, photoelectric effect, the energy is absorbed by the material. So, different material can have different, for the same energy that is going in, different material can have a different level of absorption, loss in the signal. I am not using the word attenuation yet, right, just to give a feel. So, it is, you have an energy that is reduced. So, depending on the material, the amount of reduction will take. So, the remaining will come out. So, it is this differential material's ability, different material has different ability to have this photoelectric effect, right, absorb the energy to different extents. That is what you want to map. So, you want to maximize photoelectric effect. So, if there is no interaction, whatever you send, whatever comes out, then you are not going to tell anything about the medium, right. Or other extreme, I send everything and everything is lost inside, I do not get anything outside. Then also you cannot really comment about, because your output is 0, right. So, you cannot really tell what is there inside the body. So, there is this idea that photoelectric effect helps because of this differential attenuation by the tissue materials to the X-ray energy. This photoelectric effect, which basically says that the photon is going to interact with the tissue, the material, the the cloud, that is going to be helpful factor for us, right. That is going to be our clue, signal. How does it interact with the material? If it interacts with the material, then by measuring that signal I can comment about the material, right. So, that is photoelectric effect helps in that. Then what about Compton scattering? Compton scattering, as we already talked about, right, scattering causes incident photon to go into a different direction. So, it deviates from the straight line path. So, in some sense it is unnecessary exposure will be happening, in the sense that I send the photons, it does Compton scattering. So, I am thinking I am going to get the photon energy through my body to the other side, whereas it got deflected inside the body, it goes all over the body and exits the body from some other angle. Then although all the interaction, absorption, ionization, everything took place, I am not able to even catch the signal, right. If I do not catch the signal, I cannot really get anything about the tissue or the material. So, essentially you would have irradiated the tissue with X-ray energy, but that energy interaction with the tissue, that signal is not coming out, that signal is scattered everywhere. So that is what we mean by exposure of X-ray to untargeted areas. So no, it may go into other direction and cause some ionization in some other organ. Okay, so that is so in some sense you can look at it, this is the signal that we are interested, this is a effect that doesn't contribute to our signal, in fact it contributes to difficulties, right. So this signal is kind of your noise. Okay. So in medical imaging we would like to increase the likelihood of photoelectric effect while minimizing Compton scattering. Very important, we should know what we are going after. Okay. So in some sense it is very intuitive, right. So let us take an example, how do I engineer this, right. Now that we have this knowledge, how do I exploit it? I mean the simplest case, let me tell you what happens if I know how to increase the likelihood of photoelectric events. What does that mean? Oh, I want the photons to get absorbed by the Coulomb cloud, the atom cloud, right. So what happens if I say, look, I want to increase the probability so that it actually is completely absorbed by the material, that is nothing comes out. Oh, from a medical imaging point of view we might not favor that because we need something to come, but then if you actually cleverly look at it, oh, maybe there is a way in which if I am I don't want to be affected by the ionizing radiation, then I can have a material in front of me which maximizes photoelectric effect to the extent that all the X radiations, that ionizing radiations that come, right, get absorbed in the material that is placed in front of me. That way I won't get any radiation, right. So I mean it's just knowledge. So if you know that, that's why if you go to a scan room, right, operator who is going to do all that, he will have safety because you are gone there to take a chest X-ray. He doesn't want to get exposed to ionizing radiation. That he sits in another room is one thing, but even then you will see that they will put some jacket, lead jacket. Why? Oh, because they want this energy to get absorbed by that lead jacket. They don't want to get ionized. They don't want this ionization to go to their soft tissue. Likewise, minimizing Compton scattering. If you know how to minimize Compton scattering, that is beneficial. Like just the example that we saw, the angles are coming. So we can calculate either how to minimize the Compton scattering, because from perspective of dose is one thing, the other perspective is also contributing to the noise. Okay, because I am probably looking at some signal coming straight through, right. So I'm looking at my detector is looking at some H mu that's supposed to come straight through, whereas now that is my signal of interest, but now because of Compton scattering something else happened and that one comes at an angle and hits here. So while I am looking at here, something else come and hit me here. I will not know, I will say it came from here. So basically this is noise, this is corrupting my measurement. So it is undesired, right. So I want to minimize that. So I can then in that sense come up with schemes so that I can prevent, right, Compton scattered photons to come. So I can have some ways, mechanisms through which if the signal is coming from, if the photons are coming at a certain angles, right, I would have material so that will stop the photons hitting the detector. Okay. So knowing this is very important because we will then strategically use this to our advantage. Okay. So that means we will spend a little more time on understanding what do we mean by increasing the likelihood or decreasing the likelihood, right. So it is all probabilistic. So intuitively to think about it, we are interested in photoelectric. When does photoelectric effect happen? Oh, you have a energy, photon with X-ray energy coming in. It is interacting with the cloud of electrons. So the key is it has to interact with the electron cloud or the Coulomb field, right. So when does that happen? Well, Without knowing much, I can say, oh, if the field is big, right, then I maximize the chance. The field is strong, then I maximize the chance. So that means if I have more protons, then I am going to have equal number of electrons. So more the protons, more the electrons, more the electron cloud. So I maximize my chance, right? Very straightforward extension of what we know from the definition of photoelectric effect. So more likely when colliding with an atom with more protons. So that means if it is a higher Z number, right, then you are maximizing the chance. So it's all very first order rule of thumb kind of. So we are not going to derive the details, because these are all fields, whole physics they were doing all this. So we are not going to do that. We are going to appreciate the rationale of, photoelectric effect says it is it is interacting, the energy is h mu is interacting with the Coulomb field. So if there are more electrons, if there is strong field, then there is a higher chance of h mu interacting. Okay, so we will only say that you need a higher Z number. In fact, exact order we will put, but rule of thumb is directly proportional, right? Which order we will talk about. So what we also can guess is less likely when incident photon have higher energy. Why is it very guessable? So let's go back to our example. Like I said, it's a laymanish example, but maybe the message will be sent. So recall how we said, I am the electron, I have a lot of energy, I am running, right, and there are 15 of you that they are there. Okay, so when I go, if I have lot more energy, what is going to happen? Am I going to, with relations to the people who are standing there, if I have way too much energy compared to the people there, I will not probably interact with them. When I go through them, they will all fall apart and I'll proceed further. When is the chance of me interacting with them? Oh, when my energy is not so much, it's greater than theirs, so that I will have some energy to give, right? If I don't have energy, if I have energy less than theirs, then probably I'll go, I cannot penetrate them, I'll come back. But the idea is, I am ionizing radiation, so I have enough energy, so I am going there. So what will happen? If I go there, if there are many of them, I will interact with them, I will push them, nudge them slightly, right, and then I will go further. So there is going to be interaction. The chances of interaction goes up if the energy is not way too much. So if the energy is way too much, I won't interact with them. I'll just run through, they will all fall apart, I'll keep going. So I won't lose much energy in that sense, right? So what is the fun? I send some energy through, it doesn't interact with the tissue, it comes out. What is the fun? Right? I don't get anything from that. So less likely when the incident photons have higher energy. Okay, so you have to look at some energy level that is conducive for maximizing the probability. So from an interaction perspective, from a probability perspective, one is directly proportional, other is inversely proportional. Okay, so the exact order is like here, probability of a photoelectric event to take place depends on the fourth power of Z effective. So why is this Z effective? I talked about atom, but you have some compounds, some molecules, so you have several different kinds of atoms perhaps. So Z effective is the effective average of all the atoms that are there, all the different types of atoms that are there. H mu cube. So for tissue it is about Z power 4, but if the interaction is with some material which are heavy atoms, then they say it is Z power 3. But for our purpose, we will take that probability of photoelectric event is proportional to fourth power of Z effective by H mu, the energy that is incident, right, cube of that. So lesser the energy, more the density of your more the atomic number, then your chances are increasing. Okay. beyond that, there is one more detail. The probability increases abruptly. So, this is fine, but the probability increases abruptly when the photon energy raises about the binding energy. So, all now we said okay, h mu is going in, it is interacting, fully absorbed, right. But if it turns out that this h, whatever you are sending, the h mu is sufficient or it is close to this binding energy, just greater than your L and K, then suddenly what happens is this energy is able to overcome the binding energy of the K electron, right. So, the probability of the effect taking place increases. Okay. So, the probability increases when the photon energy rises above the binding energy of K electron, right, because then suddenly you have many electrons, that Ki shell electron becomes right, you can eject them. Okay. And then of course after that it will start to diminish. So, when you have a energy such that it is close to the K shell L shell binding energy, you have maximized the photoelectric effect. So, here again, how do, naturally probably you cannot do much, right. We are composed of certain material, so they have characteristics. How do you maximize all this, engineer all this? That is where they do. If you can engineer a material, right, if you can engineer a material so that its K shell or L shell binding energy is within the range of the diagnostic X-ray energy that you are sending in. If you can engineer such a material, then probably the activity of that material will go up. Where do they engineer? You look at something called as contrast agents. We will not cover that here, but you know sometimes contrast agents are, these are agents that are there to generate contrast. That is why. So, you inject it. So, you have your angio, right, when you go for the dye, right, you would have asked, they will inject a dye and then do a CT or a X-ray, right. So, what does that do? That is a material, that material is sent in, which is carefully engineered so that its K shell L shell is just above the dose that the X-ray tube energy that is used in that imaging system. So, that when that goes in, suddenly that will behave very differently compared to the rest of the tissue. So, that you can clearly spot where all the dye is going, you will see that contrasts it out compared to the rest very easily. So, that is why it is called as contrast agents. So, you look at when you do contrast agent angio, you will see several vascular picture in CT. Those are all high contrast, very clear for that reason. Okay. So, that is for your probability of your photoelectric effect. So, then what about probability of your Compton scattering? Okay, what we know is Compton scattering, when the energy comes in, it interacts with the outer shell, or interacts as in it knocks the outer shell and then reduces the energy and it goes in another direction. So, when can you maximize that? I mean, the likelihood is if you have more electrons, the chances are that it encounters an electron at the outer level before it actually goes into the, it is attracted by the nucleus, right, or it goes towards the K electron. So, that means you have to maximize the electron density. Okay. So, likelihood proportional to the number of electrons per kilogram of the material or the electron density. What is electron density? You have right, number of atoms in a mole, and then your Z, and then your weight in mole. So, you have Avogadro number, right, you have heard of Avogadro number, right, number of atoms in a mole, right, and then you have your Z. So, that tells you number of electrons in an atom, you can get that, and then you have your weight. Okay. So, with that you can have electron density. So, it is directly proportional to, or the likelihood is related proportional to your electron density. So, probability of your Compton event is directly proportional to your electron density. And in this case it is really, I mean, at least for, I mean, these are all, there are a lot of physics that are there behind several aspects of this with respect to, for example, energy. But for the energy that is encountered in human interactions, right, here for biomedical applications, in that range it is found that relatively the probability of Compton scattering, right, that is relatively independent of the incident photon energy. So we don't have to worry. So good news is that, bad news is also that. Bad news is, irrespective of the energy you are going to work, you are going to have Compton scattering. It is something that is not desired, right? So you are going to have that irrespective of whichever energy you are using. At least photoelectric effect we can maximize. Oh, okay, if I put an contrast agent, I can tune the energy so that it is the K and L, so I can maximize my signal. Whereas here it does not depend on the energy, and therefore it's always going to be there. Okay, so that is a downside. Yeah, these are just the whatever I listed. Na is the Avogadro number, which is the atoms per mole. Z is the atomic number, and then Wm is the weight in grams per mole. Okay, so that is for your Compton scattering. So let us kind of wrap up. Right, we looked at the probability, we looked at what is signal, what is favorable, what is unfavorable, what should be maximized, what should be minimized. So ED, electron density, is approximately for biological tissue, right, approximately constant for all the material except for hydrogen, which is 6 into 10 power 26. Rest of them are all 3 into 10 power 26. So the essence is, right, you are going to have Compton scattering. It is independent of the material that you are going to see. Okay, to summarize, Compton scattering is equally likely in various materials and invariant of incident energy. So you see, so you have to live up with the noise. Actually, it's just noise. If from a signal point of view, you might say it is noise, but actually, if you really think through whatever physics we have covered, it is just not that. It is just unnecessarily you are dosing the patient, right? Because it is not even coming out to help you, but then it is is there inside the body. It is exiting somewhere, so it is actually a problem. So photoelectric effect is more likely in high Z material and less likely in high incident energy. So this kind of gives you, because intuitively what we may feel, at least without much thought, first, oh, you send more energy, maybe it will help, right? No, that is not going to happen, because your signal is not going to, number of photons should increase, but it should be in an energy where this maximum interaction can take place. That is key. So don't get confused with the example that we did yesterday in introduction. I said signal to noise ratio, right? Specifically, there we talked about square root of n. Then I said, oh, you can increase the signal to noise ratio by sending in more photons. More photon is different from energy of the photons. If you send higher energy, it doesn't help, right? So it is not, that is what this means. So overall Compton scattering is dominant with higher incident energy in the same material. So you see the disadvantage. So if you have a higher energy that you are going to use, not only that you are minimizing the photoelectric effect, you also increase the Compton scattering. Okay, and also what would be interesting to compare is what is the percentage of interaction. So if I send the energy in a given material, how much of it is Compton scattering, how much of the photons do photoelectric effect. That is one way of looking at it. That is the number, percentage of times that one is happening, the other. The other way to look at it is interactions might be same, but amount of energy that is deposited, right, that is another issue. So, there is a table in the text, which is table 4.5 of prints and links, that, and you will see there quickly that the percentage of interaction is Compton scattering is more, but the energy deposited, right, due to Compton scattering is less compared to the photoelectric effect. In fact, there is, you look at it, you will notice that even at 60% of the interaction can be Compton scattering, something like that, right. But then your amount of energy that is deposited will still, your photoelectric effect will contribute to significant deposition. So, look at the table 4.5, that tells you that it is probably in some sense it is understandable. Compton scattering, you will have many interactions, but the energy that is deposited in the tissue is less, whereas in photoelectric effect, because the principle of photoelectric effect is the energy is absorbed by the atom, right. So, naturally, even though the number of interactions of photoelectric is less compared to Compton, the energy that is deposited will be more in photoelectric. Okay. So, we will stop that here. We will now proceed further as to how do we now start to write the interaction. We talked about loss in energy. So, how do we write the loss in energy, how do we write the in terms of photons and then attenuation, all that, so that we kind of get little more detail into this, quantifying this interaction, right. We know the effects. Next question is, how do we quantify that, how do we describe that with some numbers, some equations, right. So, we will stop here and we will continue from there next. Thank you.